Okay. Last time we have stopped by the performance parameters of the transformer, and we said that if we wanna, for example, to buy a transformer from the market, there are some specific parameters or such parameters that reflect the performance of transformers. And the first one was the voltage regulation. The voltage regulation of transformer is the change in the magnitude of the secondary terminal voltage from no load to full load when the primary voltage is a constant. It is usually expressed as a percentage of the full load as. So the voltage regulation is given as a percentage, and it's equal to the no load voltage minus the full load voltage over no load voltage, of course, of the secondary, multiplied by 100 to make it a percentage. So this voltage regulation can be calculated as a value between 0 and 1, and can be calculated also as a percentage. What is the meaning of this voltage regulation? Is when we connect a load in the terminals of the transformer in the secondary, and we observe that change of the voltage. So when we connect, if we don't connect a load, of course, the secondary voltage is the relationship between the secondary voltage and the primary voltage is the TURAN ratio. But the value of the secondary voltage itself, when we connect a load between the terminals of this transformer, this voltage change. This voltage may be increase, may be decrease. It's depend on the type of the load. So the voltage regulation equals to the secondary voltage in case, or before, we can say before connecting the load, minus the secondary voltage after connecting the load. So we see the change, the load effect on the voltage over the full load voltage. Of course, the denominator is taken as a reference here, the full load voltage, or also the no load voltage here can be taken as a reference. The voltage regulation can be also expressed as V1 over A, which is the primary voltage referred to the secondary, and it has the same value of the secondary voltage in case of no load, minus full load voltage over full load voltage. Also, as I said, the no load voltage can be taken as reference, and those expressions 37 and 39 will give 37 and 39 will give the same result. Okay. So, depending on the power factor of the load, lagging or leading or a unity power factor, the voltage change, of course, when the presence of the load, which means that we have a current in the secondary. So the voltage drop of the impedance of the transformer in the secondary will be taken into consideration. We have seen when we have done a no load test that we neglect the impedance of the transformer of the primary and the secondary, because we don't have, for example, a current in the secondary because it's an open circuit. But when we connect the load, the voltage drop due to the internal impedance, which means the internal impedance here of the transformer means R, maybe R equivalent, and can be X equivalent of the transformer. So if the circuit is referred to the secondary of the transformer, here, in order to determine the voltage drop, which is delta V, which is the voltage drop, equals to no load voltage, no load, minus full load voltage. So this is the change. Okay, and the voltage regulation VR is equals to what? Equals to delta V from the previous expression. Equals to what? Equals to this one is delta V over full load, for example, voltage, full load. Okay. So the voltage can be expressed as V1 over V2 over A equals to V2 plus I2 Z equivalent. This expression can be taken from simplified equivalent circuit. For example, we have referred to the secondary, so the voltage of the primary become V1 over A, and we have a resistor, inductor, and we have a resistance. Okay, and here we have a load. So V2 is the voltage across the load. Okay, and I2 times Z equivalent is the voltage of this impedance R and X. Of course, the Phasor diagram can be shown as you see here according to this equivalent circuit. Okay, it's the same as the one we have seen in previously. Just in this case, the circuit is referred to the secondary. Now, when all quantities are referred to the secondary side of the transformer, the approximate value of the voltage, so the current that's flowing in the impedance, can be divided to I2, divided to I2 cosine theta, the current that's flowing in R, and I2 sine theta, the current that's flowing in the X equivalent, which is the reactance. Then the voltage drop, which is the difference between no load voltage, we said that V1 over A, it's the same as V2 in case of no load, minus V2 equals to I times R equivalent cosine theta plus G X equivalent sine theta. Then delta V equals to delta V can be written as, or the voltage, the no load voltage can be written as the voltage across the load plus or minus the voltage drop. This is the voltage drop, and we put plus or minus because it can be positive or negative. It depends on the type of the load. So this is concerning the voltage regulation. This is the first performance parameter. So the voltage regulation can be calculated directly from this expression. Okay, and the last demonstration is just to determine the meaning of the voltage drop, which is delta V. Now let's see the second performance parameter, which is the efficiency. The efficiency is very important in the electric machines, motors, transformers, or whatever in any system. And the efficiency simply is the output power over the input power. Also, the efficiency is calculated as a percentage. The meaning of the efficiency, as we say in Arabic, المردودية. So how much this transformer give us compared to what we have, what we give it. Okay, so we give the transformer a power in the input. So how much the output power according to the input power. Okay, so the efficiency never exceed 100% because we are not in the ideal transformer. If we have ideal transformer, maybe the efficiency can be found as 100%, but there is no ideal transformer in the reality. So the efficiency always less than 1 or less than 100%, which is equal to the P out over P input, which is P is the active power, of course. And also the input power equals to what? The input power equals to the output power plus losses. So why the sum of losses? Why the output power less than the input power? Because there are losses have been taken from the input power, which are the core losses and the copper losses. So here the input power can be written as output power plus the sum of losses, and the sum of losses is the P out plus the core losses plus the copper losses. So the core losses plus the copper losses are the sum of losses in the transformer, and we can demonstrate it as let's draw a diagram, which we call it the power flow diagram, to clarify more the meaning of the losses, how the losses has been taken. For example, if this is the power, okay, if this is the power, input power here, P in, and this is P out. So this power, this is the input power, and this is the output power. So when the power enters to this transformer, losses will be taken from this power. Starting, for example, firstly we are going to take the copper losses, for example, in the copper losses in the primary, P copper in the primary. Then we're going to take also the core losses, P core. Then we are going to take also the copper losses in the secondary, because we have impedance, equivalent impedance in the primary and in the secondary. Then we are going to get the output power. So the output power, of course, always the output power always less than the input power. This is the meaning of, we call this power flow. So power flow. Okay. So this is the efficiency. Of course, when we, for example, if we want to buy a transformer, always we try to choose the transformer that has the maximum of the efficiency. For example, 90% or 95%, which means that this transformer has low losses. And those losses, of course, depends on the materials the transformer are made from. Of course. Also, in term of active power, that also the efficiency can be written as V2 I2 cosine theta over, which is the output power, plus the output power, which is V2 I2 cosine theta, plus core losses plus copper losses, times 100% if we want to calculate it as a percentage, or we can calculate it as a value between 0 and 1. So it's correct in both cases. Of course, the copper losses equals to the copper losses in the primary plus the copper losses in the secondary. And we have seen the short circuit test and we have determined the copper losses, which are equals to what? Equals to the current of the primary times R equivalent 1 if the circuit referred to the primary, or the current of the secondary times R equivalent 2 if the circuit referred to the secondary, and equals to the short circuit power. So the short circuit power is almost the copper losses. Why? We are neglecting the core losses in the case of a short circuit test. We said the effect of core is almost neglected in case of the short circuit test. So the copper losses are calculated in the short circuit test, and the copper losses P copper are taken equals to P short circuit. Okay, this is a remark. The current, voltage, and the equivalent circuit parameter must be referred to the same side of the transformer. Of course, we work with the primary or we work with the secondary. We don't mix. Okay, this is concerning the meaning of efficiency. I think those concepts are simple because they are just a direct application. Now let's see a maximum efficiency. So when the efficiency is maximum of the transformer for constant value of the terminal voltage V2 and the load power factor theta 2, the maximum efficiency occurs when, of course, this has proof, but we don't have time to prove it. So the derivative of efficiency over by derivating the efficiency over the secondary current, we're gonna get this expression. So the efficiency is maximum when the copper losses are equals to the core losses. Okay, but here let's just make a difference. Sometimes the transformer work on full load. What does it mean? What does it mean full load? The maximum load that this transformer can support. So the current in case of the full load is the rated current. And sometimes, for example, this transformer work in half load or in 25% from the load. We don't know exactly where the efficiency is maximum. Is it with the at full load or half of the load? So when the efficiency is maximum is when the copper losses equals to the core losses, and this expression has a proof. Maybe I will show you the proof in the recitation. I will try to see, because there is a proof, but I didn't put it here in the course. Maybe in the recitation, inshallah, we're gonna see this proof if we have time. But the condition here of the maximum efficiency, when the efficiency is maximum, so it can be given even as a question. When the efficiency of the transformer is maximum is when the copper losses and the core losses are equals. So this is concerning.
Sir, can you repeat what you said about the derivative of the efficiency?
Okay. The derivative here, this is the beginning of the proof, and this is the end of the proof. Okay. So how can we determine that okay, let's check it. Just one.
But the derivative needs to equal something, no?
Normally equals
equal zero, no?
Equal to zero, yes.
Yeah,
I think something is missing.
Yes.
Normally it equals to zero. Okay. Let me check it. Okay. Excuse me. Okay. efficiency, transformer efficiency. Okay, no, the proof is not in this textbook, but I will check. Normally, it's equal to 0 when this derivative is equal to 0. I think I have taken it from another textbook. Okay. When this derivative equals to 0, we will have P copper equals to P core. This is the condition of the maximum efficiency. Also, we are going to define another thing, which is the all-day efficiency. What does it mean, all-day efficiency? Before, you know the difference between the power and the energy. We may talk about it before. The energy, for example, in joule, or in it has many units. The energy equals to the power times time. P times T. This is the energy, and also it can be measured in watt hour, for example. Okay. So the all-day efficiency, since the transformer are connected, the transformer that are connected in the power system, they work all the day. So they work 24 hours in the day. Okay. So since transformers are connected to the power system a day and operate well below rated power, the distribution transformer will that supply the electricity, for example, on our houses, evaluated by the all-day efficiency. So the all-day efficiency equals to what? Equals to the output energy measured in kilowatt hour, which means the power times time. The power times time over the input power times time. And here the time is 24 hours. So this is the all-day efficiency. The all-day efficiency equals to the energy, the output energy, in 1 hour, in 24 hours. So if the transformer is not working 24 hours, we're going to choose any moment, any period. We have an example, for example. We have an example for this in the recitation, 6 hours, 8 hours. Just the power times time. Here, in case of the distribution transformers that are placed in the power system, they work 24 hours per day. But maybe you will have a transformer in your house, maybe it's not working 24 hours per day. Okay, so the output energy over 24 hours, kilowatt, which is the unit of the power, times hour, which is the unit of the time, over the input energy, which is also measured in watt hour or kilowatt hour. This is the meaning of the energy, which is the power times time, and the all-day efficiency is the output energy over the input energy. That's why 24, because we call it all day. This is the last element in this part. So before passing to the next part, which is the last part, part 3 of this course, which is the autotransformer and the 3-phase transformer, we are going to see an example. Consider 100 kilovolt ampere single-phase transformer. The high voltage power is 7,200, and the low voltage power, the high voltage is 7,200, and the low voltage is 240 volts. The frequency is 60 hertz. Assume that the open circuit and the short circuit were performed on the transformer, and the following data were obtained. So here, the open circuit has been done. The open circuit and the short circuit has been done, and those are the measurement has been taken. This is the voltage, the open circuit voltage, the open circuit current, and the open circuit power. This is the short circuit voltage, the short circuit current, and the short circuit power. Also assume that the transformer operates at full load with 0.9 lagging power factor. Determine the following: the equivalent impedance, resistance, or reactances of the transformer referred to the primary. Total losses, including the copper losses and the core losses at full load. The efficiency of the transformer, the percent voltage regulation of the transformer, and the Phasor diagram. So we can see that example include everything we have seen previously. This, especially in this second part. So this example include all things we have seen.
Sir, please.
Yeah.
When we say open circuit on primary, does it mean like we open the primary?
No, open circuit on the primary.
Yes.
No.
Where we open?
No. Okay. Let's don't mix between when we said primary and secondary, and when we say high voltage and low voltage. Okay.
Yes,
so
sir.
if we choose the part where we place our measurement devices is the primary.
Yes.
And the other part, let it open. Okay. So the measurement has been done in the primary. Okay, whatever if it's high or low voltage side. And here
Yes,
they choose.
my problem, I don't know where to open. Like when we have open on primary or open on secondary, I don't know exactly where to open. Can you please show us?
Okay, so there are some questions. Okay, concerning the maximum efficiency. The maximum efficiency does not have a load. It has a condition. Okay, when the copper losses and the core losses are equals, we achieve the maximum efficiency. Okay, so it has a condition. So when we find that condition, that the copper losses equals to the core losses, it means that we have a maximum efficiency. We are going to see, inshallah, examples concerning this maximum efficiency. Okay, let's see what we have seen before. Okay, in our tests, for example, this is the open circuit test. When we said in the primary, of course, the measurement, which means that the measurement has been done in the primary. That is the primary voltage, the primary current, and the primary power. Okay, and this the secondary, we let it open or place a voltmeter, as I told you. Also, concerning the short circuit test, we place our measurement devices in the primary, and we place in the secondary a meter or can be a wire. Okay, so which means they said primary, which means that the measurements, those measurements are primary measurement. Okay, those measurements are the measurement has been done in the primary side. And here, because it may be confused between primary, secondary, high voltage, and low voltage, we said that the low voltage can be primary or secondary. Also, the high voltage can be primary or secondary. Here they choose the high voltage as primary, which means it's a step-down transformer. Okay.
Yes, sir. My question, please, it was like if it was an open circuit test on secondary.
It's open. The secondary is open.
If it was an open circuit test on the secondary, I mean, where it is written on primary, it was written on secondary. Is it possible?
Yeah. If we do open circuit on the secondary, that secondary become primary.
Okay.
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 So the input voltage from each side, we choose the side to give a voltage. Okay.
Exactly. Yes.
Okay. So let's see. Yeah. Yeah.
But as Mahfoudi said, like if we put secondary instead of primary,
So
the voltage. Yes, I know. We will apply the same rules, but the voltage will be different. I mean, the voltage of the
Yes.
secondary.
Yes, sure, yeah. Okay.
Thank you.
Okay. So let's see the solution of this exercise. Firstly, the equivalent impedance referred to the primary. The equivalent impedance, which means the Z equivalent. So the Z equivalent has been determined in the short circuit test, of course. Let's try to do it on the table. Okay, let's try to do it on the table. Okay, so the equivalent circuit in case of short circuit tests, we have a resistance, which is the equivalent resistance, and we have inductance, which is the equivalent inductance, and it's shorted here. So this is the voltage, and this is the current referred to the primary, I1, V1. And here, of course, in case of the circuit referred to the primary, R equivalent equals to what? Equals to R1 plus A R2. And X equivalent equals to what? Equals to X1 plus A X2. Okay, so let's see. Firstly, the equivalent you have proved before, the equivalent impedance equals to, using the measurement in case of the short circuit test, directly is equal to what? Z equivalent measured in the short circuit. Okay, Z equivalent equals to Z short circuit. Okay, this is the internal impedance of the transformer. Okay, and equals to what? Equals to V1 or V short circuit, V short circuit, V short circuit over I short circuit. Okay, and here according to the data, V short circuit is 250 over 13.889, and this is equal to what? Equals to 18 ohms. This is the value of the equivalent. Also, after determining Z equivalent, we determine R equivalent. We know that the short circuit power equals to what? Equals to the copper losses, and these copper losses equals to what? Equals to I short circuit square times R, which is R equivalent. Then R equivalent equals to what? Equals to the short circuit power over I short circuit square. Okay, so the short circuit power is given as 1420 over what? Over 13.889 square, and it's equal to 7.36 ohm. Then after calculating Z equivalent and R equivalent, X equivalent equals to Z square minus R square root. Okay, and it can be done like this. So those three parameters has been calculated using the measurement of the short circuit tests. Okay, so we have to make a difference which data we are going to use. It's depend on the equivalent circuit, of course. So the short circuit test will determine the internal impedance of the transformer, which is the impedance, the resistance, and the reactance of the winding of the transformer. Now let's calculate the copper loss and core losses. Of course, directly the copper losses are the short circuit losses, as we have. It's given here. It's given here 1,420 watt, and when we check it, we found what? We found that the copper losses equals to what? Equals to I square times R, and it's almost the power measured. Why it's not? It's almost because the core losses are neglected in these tests. The core losses will be calculated in the open circuit test. Okay, so we checked here that the copper losses are almost equal to the short circuit losses, which is given as 104,020. Okay, so it's 19.98, which is almost equals to 20. The core losses are equal to the open circuit power, which is given as in the Yoga state test, which is given as 425 watt. Okay. So directly, the copper losses and the core losses are the short circuit power and the open circuit power. Here, for example, in this case, we have resistance. We have the value of the resistance. That's why we have calculated that like this. But if we, for example, if we don't have the value of the resistance or the value of the current, we take it directly that the copper losses are equals to the short circuit power. If we don't have current or resistance. If we have current and resistance, we can measure it, and it's almost the same. So those are the copper losses. Okay. The total losses. Okay. Before passing to this, the short circuit current. Okay. What does it mean here when they said full load? When they said full load, which means that we use the rated values. Okay, so the current reach its rated value when the transformer operates in full load. Okay, so the maximum. Okay, so it's the maximum load that the transformer can support and work normally. So it can support overload, but for a short moment. Okay, so it cannot work overload for a long time. But the full load, which means that the maximum load that it can work with normally. Okay, without a risk of damage, or for example. But overload, it may be cause a damage of the transformer. So it may be work overload for a short moment. But when we said full load, which means that work with rated current. So that's why here to calculate the rated current, we use this expression, which S over VI, and we found 13.89, which is equals to what? Equals to the short circuit current. So in the short circuit current here, they give the rated current. They cannot exceed this rated current to avoid the damage of the transformer. I told you that the short circuit test must be done in short time. So here the short circuit current is equal also to the full load current or to the rated current. So the rated current is the same as a full load current, and it's almost the short circuit current. Okay, let's check if we have questions before. Okay, I said we didn't have because we have R. We calculate again the copper losses. If we don't have R equivalent or I equivalent, we can take directly the short circuit power. It's almost the same. The same thing with the current. Okay, so the rated current here has been calculated from S and V, and it's almost equal to the short circuit current. So the total losses equals to what? Equals to the core losses plus the copper losses, and it's equal to 1,844 watt. Now the efficiency. The efficiency of transformer, we said that equals to what? To find the input power, let us find the output power first. Okay. We said that the efficiency equals to what? Equals to P out over P in, and equals to what? Equals to P out over P out plus the sum of losses. Okay, let's draw it in the table. Here is just a remark. When we talk about the efficiency, the calculation of the efficiency, always when we have load, okay, we cannot calculate the efficiency, for example, in the short circuit test or in the open circuit test, because we don't have a load. When we talk about the efficiency, which means that we have a load here, assume that the transformer operates at full load with 0.9 lagging power factor. So this is our load. We cannot calculate the efficiency if we don't have a load, because if we don't have a load, we don't have an output power. Okay, okay. So this is the efficiency. Equals to what? Equals to P out.
Sir, what do you mean by a full load?
I said it many times. The full load is the maximum load that the transformer can support. So when we connect the load at its full value, the current will be at its rated value. Okay. So this is this load depends on the characteristic of the transformer. For example, when we bring this transformer, we see the maximum of the current. For example, they said we cannot exceed, for example, 10 amps. So we cannot connect a load that consume more than 10 amps to this transformer. Okay, because the current always depends on the load. V, according to Ohm's law, of course. V over R equals to I. Okay, so the current, the load, which the voltage, of course, is this transformer is a voltage source, which means that the voltage is constant, but the current depends on the load. We cannot connect a load to the transformer that require or that consume more than the rated current. And the rated current of the transformer, we can find it on the transformer, on the nameplate. Okay, I will try to find the nameplate. Okay, let's Google nameplate of transformer. Okay, to show you the meaning of the nameplate of the transformer. Okay, so this is the nameplate. Okay, we found it on, place it on the transformer. Okay, so those are nameplate of the transformer. Here we can find information concerning voltage and the current. Okay, no load, full load. Okay, so it's contain information concerning those transformer. Of course, we are talking about when we have real real transformer, of course. Okay, so this is the nameplate. Okay, let's see this one. I hope it's clear a bit. Okay, let's see this one. Okay, so are you seeing this nameplate here? Okay, we can see here, for example, HV amps, which means the current in the high voltage side is 10.5, and LV amps, the current in the low voltage side is 278.2 amps. So this is the rated values of the current. Okay, so when the current are at this value, we can say that the transformer is operating on full load. Okay, how we? Okay, so it's not problem. If it's not a full load, they will inform you that it's not a full load. Okay, I said we calculate the efficiency. When we have a load, does not mean it is necessary to be a full load. Okay, it's not necessary to be a full load. For example, I can give you calculate the efficiency at half load, for example, or at 25% of the load. Okay, so we said, of course, the current will change because we change the load. So this is the nameplate. In the nameplate, we are gonna find the rated values. For example, voltage, currents, and there are other informations, frequency. Okay. Okay, let's go back to our exercise. We said that we calculate the efficiency when we have a load. So P, the efficiency equals to P out over P in, and it's equal to P out over P out plus the maximum plus the sum of losses, P out, or the P of the secondary, plus the P losses. Okay, so this is how we can calculate the efficiency. Okay, so the efficiency of the transformer. To find the input power, let us find the output power first. So we have the sum of losses. Let's find now the output power. Then, okay, so the output power, since we have the apparent power, of course, the apparent power, it's the same in the primary or the secondary. We don't say that this apparent power of the primary or of the secondary. The apparent power is conserved on the primary or on the secondary. So we have the S, which is the apparent power S, which is V times I, and it's given here in our in the data 100 kilovolt amps, and we have cosine phi, which is 0.9, the power factor. So the output power, of course, this one is for the secondary, because they said full load. Of course, the load is connected to the secondary with 0.9 lagging power factor. So P equals to what? P out is the P2. P secondary equals to S times cosine theta of the secondary. Theta is given as 0.9, cosine theta is given as 0.9. So P out equals to S cosine theta and equals to 100,000 volt ampere times 0.9 and equals to 90,000 watt. This is the active power. Then the input power can be found as P out plus the total of losses. So it's equals to 91,845 watt. Then the efficiency can be calculated as here, for example, this is another expression, but we can directly put 990 over 91, or this is another expression can be driven like this. We have output power over output power, output power plus the maximum of losses. Okay, so this is expression can be driven from this one. You can find it 1 minus total of losses over P. Or we can calculate directly. Okay, don't confuse yourself with this expression. It can be driven easily. Okay, directly you can check it. The efficiency equals to what? Equals to 9,000 over 91,000, and it's equal to 97%. So it's a high efficiency. Mostly the efficiency of transformers is high compared to motors, for example, because in the motors we will have another type of losses, which is the mechanical losses, because the motors, they have a rotation part, a moving part. They have core losses, copper losses, plus the mechanical losses. In transformers, we don't have a mechanical losses. That's why the efficiency of the transformer almost is high. So here the efficiency is 0.97 or 97%, if we want to take it as a percentage. Okay, so is it clear here concerning the efficiency? Before passing to the next question. Okay, so now let's the next question is calculate the percent voltage regulation of the transformers. So we have seen the expression of the voltage regulation here. The expression we have seen before is when the circuit referred to the secondary, but in this case our circuit here is referred to the primary, but always it means that voltage regulation is the difference between no load voltage minus the voltage across the load. Okay. Okay, let's see here what we have done. Okay. Okay. here before calculating the voltage regulation, we have to determine the voltage drop, okay, which is equals to what? Equals to, here the circuit is referred to the primary. Okay, here the circuit is referred to the primary. Of course, we have a load. Here the circuit is referred to the primary. So this is the primary voltage, which is V1 equals to what? Equals to A V2, which is the secondary voltage referred to the primary, plus the voltage drop of the internal impedance. Okay, and here, okay, let's check something. I think I have confused with something. Okay. Okay, that's okay. So the primary voltage equals to what? Equals to the no load voltage plus the voltage drop. Of course, here the current shifted by the angle of 125, of course, has been found from the power factor. So the angle, if the cosine -1 of 0.9 is -25, and the values of R equivalent and X equivalent has been determined from the previous tests. So the voltage here, the voltage drop has been added to the no load voltage. So this is the full load voltage. Then we have calculated the voltage regulation. Of course, here we said that the reference can be changed. Okay, we can choose the reference as no load or a full load voltage, and it will give the same result. Okay, so here we have to calculate the voltage drop, the effect of adding a load. So how it can this load, how it can affect our transformer. Okay, so since it's lagging power factor, we have seen the Phasor diagram of the lagging power factor, how it can be drawn. Okay, this is concerning the voltage regulation. Okay, and this is the last thing in this part before passing to the next part. Any question concerning this exercise? Yes. Shall we pass to the next part? Okay, so the next part is some kind of demonstration. Okay, it's a definition more than analysis, not like we have seen in this, especially this second part with equivalent circuits. And okay, shall we pass to the next part? Well, we can yes. Yes. The phasor, yeah. We have negative voltage regulation in case, I think, when we have a leading power factor. Okay, so the angle will be in the other side. The phasor, how we get it? I think you haven't seen before how we have drawn the phasor. Okay, so I will repeat it. Okay, so of course, before drawing the phasor has been drawn based on the equivalent circuit, of course, referred to the primary or to the secondary. So in case if the circuit referred to the primary, this is, for example, inductor, and this is resistor, and this is the load. Okay. In our case, the circuit is referred to the primary. So this is the voltage of the primary, V1, and this is the voltage across the load, which is the secondary voltage referred to the primary, V2 times A, and this is the current of the primary, I1, and this is R equivalent 1 and X equivalent 1. The phasor, of course, we said always we choose a reference, which is here. Our reference here is the input voltage. The voltage is here is horizontal, so the angle of the voltage is 0, and the current is shifted by angle. The current is shifted by an angle theta. Okay. The current here is shifted by an angle theta. So this is the angle theta. Now, so this is V1. This is sorry, this is V. I just get confused. This is AV2. AV2. This is AV2. This is the voltage across the load. Now, the voltage drop here across the resistance, which is I1 R equivalent. This one is voltage drop. So it's in phase with the voltage drop is in phase with the current. This one is the current. The voltage drop is in phase with the current because it's the current multiplied by R, which is the resistance. So it's in phase with the current. So let's try to do it in the same color as the current. So it's in phase with the current. This is the RI1. Then the voltage drop of XS will be shifted by 90 degrees because it's inductance. Of course, it's shifted by 90 degrees from the input voltage is what? We start from the first point to the last point. Okay, we do this always in the vector summation. Okay, so here we can get the diagram. Always just remember that we have voltage drops. The voltage drop of the resistance is in phase with the current, so it's shifted from the voltage, and the voltage drop of the reactance is shifted by 90 degrees from the voltage drop of the resistance. Then we can draw the voltage, the input voltage, from the first point, from the beginning to the end. So this is concerning the diagram. Okay. So those things can be saved in your mind with more practice. Today, the number of participants is very low. I don't know why. You are just 30. No problem. Okay. Now, so let's pass to the last part of this chapter, which is we are going to see we are gonna see 2 points quickly. And this part I just added it recently. It's not uploaded. It's not uploaded on the e-learning platform. I will upload it later, because I was thinking to do not add this part, but after that I think you should know just information, because this part is some kind of demonstration more than analysis. Okay, so let's see some special transformers in this third part. Okay, so in this third part we are going to see the autotransformer and the three-phase transformer. So the autotransformer is an okay, so I think some of you okay, concerning the platform, they change the password, I think, for all courses. I didn't check it today. Okay, I think some of you have done at least one lab session. Not the password. It's not working. Maybe their server is down. You know, those technical problems. I will check it later. Okay, I think some of you have done okay, managed. Okay, she said it's not the problem of the password. Okay, so I think I said just some of you have done a lab, and you have seen that power supply inside. You have seen those, which are the auto transformers. So they are the transformer with slider that can change the value of the voltage. Okay, so part 3, auto transformer and three-phase transformer. So the auto transformer is a single coil transformer in which the primary and the secondary are connected to the same common winding. So the auto transformer, instead of having a primary here and the secondary, as you see in here in the figure 24a, it has one common winding between the primary and the secondary. Therefore, it does not provide an electrical isolation. Okay, so this transformer does not perform that physical isolation. We said that the primary and the secondary of the transformer generally are not connected only with the flux. But here in the auto transformer, they are connected because they have a common winding. So this is the difference from how we can pass from the conventional traditional transformer with 2 winding to the auto transformer. Okay. So the auto transformer does not provide the electric isolation and cannot be used when we have, for example, when we need an isolation, we cannot use an auto transformer. However, the principle of operation is the same as a 2-winding transformer. So the advantages of auto transformer are lower leakage reactances, low losses, lower excitation current, and the disadvantage of auto transformer, so there is no isolation between the primary and the secondary. They are connected to each other. Okay, so why we use this auto transformer? So if we put slider here in this point, we can obtain a variable voltage. Okay, so this auto transformer is transformer that can provide different voltage values. Okay, of course, so the output voltage can be varied over from 0 to V1. Okay, so of course V1 is constant. So if we put slide in this side, we can obtain variable voltage. And of course, this autotransformer can be also step up and step down. And the rule, of course, is the same. So the turn ratio is V1 over V2, and it's equal to N1. So this is N1 over N2. So N, it's the same winding, but N1, the number of turns from A to C, AC, and N2 is the number of turns from B to C. So N1 equals to N2 and equals to NC, which means the common winding, the winding between B and C. We call it a common winding because it's common between the primary and the secondary. And NS, which is the series winding, the winding between A and B, over NC, which is the common winding. So using the same rules of the conventional transformer, here we can obtain a variable voltage with the same turn ratio. A equals to V1 over V2, and it's equal to N1 over N2. We said N1 is the number of turns from A to C, and N2 is equals to the number of turns from B to C, the auto transformer. So it's transformer with slider. Okay, so this part can move up and down to change the amount of voltage. So if this one is N1 and this one is N2, so this part is N1 minus N2. So this is the primary winding and this one is the secondary winding. Okay, so however, in the transformer, in the auto transformer, since the primary and the secondary are not isolated. Okay, so before, okay, let's remind. So we said in the conventional transformer, the voltage, what is the principle of operation of the transformer? According to Faraday's law, the voltage, okay, in the conventional transformer, this is conventional transformer. Okay, so according to Faraday's law, the EMF, the induced EMF equals to what? Equals to d phi over dt. So the voltage across the primary will create flux. That flux, when to get the secondary, it will create another induced voltage here according to the same rule, which is the Faraday's law. So the EMF here is d phi over dt. Of course, here we have a number of turns and sometimes d phi over dt. This is the principle of the conventional transformer. However, here the power of the transformer, of the auto transformer, will be transferred in two ways. It will be transferred by the induction according to Faraday's law, and also it will be transferred by conduction because those parts are connected. Okay, so the power here transferred from the primary to the secondary in two ways, by conduction and by induction. Induction, which means the voltage will be created. It will be created according to Faraday's law. And by conduction, because we have a current, this current of the primary, we will pass also here to get to the secondary. So here the power will be transferred in two ways. In the same time, it will be transferred by induction and by conduction. Is it clear, this point? Okay. The difference between conventional transformer and the auto transformer. Here in the autotransformer, the primary and the secondary are not isolated. They are connected to each other. That's why the power, it will be transferred by induction according to Faraday's law, and by conduction, because those parts are connected to each other. Let's continue. So the MMF provided by the upper half, this is the upper half from between A and B. The MMF AB equals to what? Equals to N1, N2, because the number of turns here is N1 minus N2 times I, according times I according to Ampere's law. And this equals to what? If we take N1 as a common factor from this, if we take N1 as a common factor, we're gonna have 1 minus 1 over A, because A equals to what? Equals to N1 over N2. So this is the EMF between A and B, the upper half. This is the EMF in the upper half. In the lower half, between B and C, the EMF equals to what? Equals to N2, the number of turns between B and C, times the current. Here the current that flowing in this coil, it's in opposite direction, because here we have an induction. Okay, here it's some kind, it's like a source. Here it's like a source, so the voltage is created here. Okay, that's why the current in this coil is in this direction. Okay, so here I1 is the primary current. I2 is the secondary current, but the current here in this coil is I1 minus I2. So maybe when you see here, you think that the current, this one will be flow in this, it will be flow in this direction, like this. You think that the current will be flowing in this direction, but it's not, because here we have a voltage created by induction. Okay, so the voltage will be created in this direction. The voltage, it's like a source. The voltage is created in this direction. That's why the current in this coil is in this direction. And this current is, we can call it Ix, for example, equals to what? Equals to I2 minus I1. I2 is the load current, or the secondary current, and I1 is the source current, or is the primary current. So the MMF between the point B and C equals to the number of turns, of course, of this coil, times the current that flowing in this coil, which is I2 minus minus N1. I think, let's see. Okay. And here, astaghfirullah. Yes. Here, how we get this expression, it has been multiplied by, I guess it has been multiplied by, astaghfirullah, how we get this one. Okay, let's see in this table, in the table. So the EMF, according to this expression, N2 equals to what? N2 equals to I2 minus N1, and this one equals to N1 over A. How we can pass from this expression to this expression? Okay. I think they multiplied it by N1 over N1. Okay. Yes. They multiplied it here by N1 over N1. So when we multiplied by N1 over N1, we are doing nothing. But N1, N2 over N1 became 1 over A, and we still have N1. So N1 over N1, it's equals to 1, of course. So they multiplied it here by N1 over N1, and we get N1 over A. So why we are doing this? Just to get to this expression. So for the MMF balance, so if we consider that the MMF produced in the upper half equals to the MMF produced in the lower half, so this one equals to this one, we are going to get this expression here, just in order to prove that the relationship of the TURAN ratio, it's the same as the conventional transformer. So we seen before that A equals to V1 over V2, and it's equal also to A1 equals to A2 over A1. So 1 over A is A1 over A2. Okay, let's continue. I think, okay, I will repeat this part, maybe you get confused. Okay. I will. So we said in the autotransformer, the power will be transferred from the primary to the secondary in two ways, by conduction and by induction. In the normal transformer, the two-winding transformer, the power transferred only by induction, by Faraday's law, by the flux. We don't have a connection between the primary and the secondary, but here the primary and the secondary are connected to each other. That's why the power will be transferred by induction and by conduction also. Here we said that the input current I1 and this is the output current or the load current I2. And since here we have an induction, a voltage will be created in this part. So the current here that flowing in the coil BC is in this direction. So the current flowing in this coil is I2 minus I1. By calculating the MMF in the upper half and the lower half of this autotransformer, we proved this, that I1 over I2 is 1 over A. So from 52 and 56, it can be seen that the voltage and the current are related by the same turn ratio as the two-winding transformer. So the general rules of the transformer are the same, but the principle of operation is different a bit. So here the power in the autotransformer will be transferred by, we said, two ways, which are the conduction and induction. Induction by the flux, by Faraday's law, and conduction by connection through wires or coils. Okay. So the power transferred by two ways. Here, if we want to calculate output power of the transformer, of course, the output power, which is the apparent power here, equals to what? Equals to V2 over I2. This is the secondary voltage times the secondary current. This is the output apparent power. However, since we said that we have a common here, a common coil, the output current equals to what? Equals to the current I1 came from the primary plus the current IX, which equals to what? Equals to I2 minus I1, the current here. So by replacing I2 by its expression here, I2 equals to I1 plus IX, we said the current came from this side and the current came from this side, and will be give us I2. By replacing I2 by its value, the output apparent powers equals to what? Equals to V2 over I1 plus V2 over I2 minus I1. And here we have two apparent power, the apparent power of the conduction and the apparent power of the induction. Okay. So this is the apparent power of the conduction. Why? Because here the current I1 came directly from the primary, came directly to the secondary. But this current here has been created, has been induced. Okay, so this is the induction apparent power. Okay. I hope you are not confused with those. Okay. Is it clear or not? Yes. I need another yes. Okay, good. Okay, good. So I will repeat. Okay. Sorry, I just left the meeting. Okay. Let's go back to the presentation. Okay. Okay. So let's repeat this part. We said that the power of the autotransformer transferred from the primary to the secondary. Okay, let's check my microphone. Is it open? Yeah. Okay. We said that the power from the primary to the secondary here in the autotransformer will be transferred into two ways: by the conduction and by induction. Why? What do we mean by induction and induction and conduction? Conduction is this way. The current I1 came directly from the primary to the secondary, directly. So this is a connection, which means a connection. But the current here, Ix, will be created, will be induced. Okay. This current here will be induced by the induction, by Faraday's law. Okay, so the current of the secondary, I2, equals to what? Equals to I1, the current from the primary, and the current has been created in this common, we call this common, which means mushtarak, in this common part, Ix. Okay, so here the current came from two ways. The first current came directly, and the current 2 has been induced or created because the voltage has been induced. Okay, so when we want to calculate the output power of the autotransformer, S out, of course, it's the secondary current times the secondary voltage directly, but V2 times I2. I2 equals to what? Equals the current came from the primary and the induced current. I1 plus Ix. I1 equals I1, and Ix is I2 minus I1 because it's in opposite direction with I1. So the output apparent power equals to what? Equals to V2 I1 plus V2 times I2 minus I1. The first part, or the first term, is the conduction power plus the induction power. So S cont is the conductively transferred power. So it's a conductively transferred power. It has been transferred by wires. Induction is the inductively transferred power. This power has been induced. So this power equals to V2 I1, and this power equals to V2 I2 minus I1. Okay, so here now let's do a comparison between the power of the autotransformer, and we compare it to the power of a conventional transformer. From this expression, for example, here it's not 52, it's 59. Okay, from 59, the output, the power here, it's the power of the autotransformer equals to what? Equals to V2 times I1 plus I1 plus I2. So here, when we distribute V2 here, okay, if we distribute V2 here, we get V2 times I2 and V2 times I1. So this one, V2 times I1 minus V2 times I1, we're gonna have what? Sorry, I think I had made a mistake. Yes, I think I had a mistake here. Okay, V2. I think I had a mistake here. Okay. Manage. Okay. I will check this part. I will check this part later. Okay, let's move to the next part, which is the last part. Okay. This part will be checked. This part will be checked later. Okay. So here, just I said that this part is just some kind of definitions. The power here has been transferred by a conduction and induction, and the power of the conduction is V2 times I1 plus the power of the induction is V2 times I2 minus I1. Okay, so let's now pass to the three-phase transformer, which is the last part here in this chapter. Okay, so almost power generation and distribution systems today are in three-phase, as we have talked many times, especially in the power system. The three-phase transformers can be constructed simply by connecting three single-phase transformers. So we can create a three-phase transformer by connecting three single-phase transformers, or we can have a three-phase transformer with a common core like this. So this is the core of a three-phase transformer. So this one is the primary, this one is the secondary of the first phase, this one is the primary, and this one is the secondary of the second phase. And this one is the primary, and this one is the secondary of the third phase. And this figure show the construction of three-phase transformer. So the three-phase transformers can be constructed simply by connecting three single-phase transformers, or by constructing a three-phase transformer in common magnetic structure, as shown here. Here, in the three-phase transformer, we're going to take only a single point, which is the connection. Okay, we are not going to see the analysis of this of the three-phase transformer, because it can be done in similar way. We can just take one phase, and we do our analysis as a single-phase transformer. Okay, so we are going to see only the types of connection of the three-phase transformer. So the primaries and the secondaries of the transformer can be connected either in Y or delta. We have seen the Y and delta connection in our first chapter. This gives 4 possibilities of connection of the 3-phase transformer. So we have primaries and secondaries. They can be connected in Y or delta. So we will get 4 types of connections. Y, which means Y in the primary, Y in the secondary. Y delta, Y in the primary, delta in the secondary. Delta Y, delta in the primary, and Y in the secondary. Delta delta, which means delta in the primary and delta in the secondary. So those are the 4 types of the connection. So here it's Y connection. We have seen the difference between a Y and delta connection and the voltage and the current relationships, and the difference between the line voltage and the phase voltage, or we can call it line to line, line to ground, or phase to phase, or phase to ground. So this is Y connection. This one is Y delta connection. Normally we have a lab in our program. We have a lab of these connections. This is delta Y connections, and the last one is delta delta connection. Those are the 4 possible connections of 3-phase transformer. Okay, concerning autotransformer, I will check that part. I know that I made the mistake on somewhere. Okay, let's continue. Those are the 4 types of the connections of the 3-phase transformers. So it's Y delta, delta Y, and delta delta. So the first one, delta Y delta connection. This connection is commonly used for the step down. So use it in the step down transformer from high voltage to low voltage. We know that the voltage in Y is more than the voltage in delta, because we have phase to phase voltage and we have phase to ground voltage, while in delta we have only 1 voltage. So this connection is commonly used to step down from high to low voltage, where the neutral point is in the high voltage side, can be grounded. Delta Y connection, this connection is commonly used for step up voltage transformer. Delta delta connection, this connection has the advantage that 1 transformer can be removed and the remaining 2 can continue to deliver 3-phase power at reduced rate of 58%. This is known as open delta connection. So when we have delta delta connection, this one, when we have delta delta connection, this connection has an ability to work with 2 transformers. We said that 3-phase transformer, it can be constructed by 3 single-phase transformers. This delta delta connection, for example, we can remove one here and a coil here, like this one, and we call it open delta connection, or we can call it V connection because it's like V. Okay, it's like V. So this type of connection can be worked with 2 transformers, because we have removed 1 transformer, but at reduced level of the power, 58. So this connection can be worked, for example, if we have if one of these transformers need maintenance or need to be replaced, or we have it has been damaged, this system can continue working with 2 transformers. So this case, the advantage of delta connection. So this connection has the advantage that 1 of the transformer can be removed and the remaining of 2 can continue to deliver 3 power at reduced rating of 58%. This is known as open delta or V connection. Okay, so this is the open delta connection. The last one is YY connection. This connection is rarely used because of problems with exciting current and induced voltage. So this is the fourth one. It's rarely used. So here we have Y delta used mostly for step down voltage, delta Y used mostly for step up voltage, and delta delta has the ability to work with two transformers. So we can remove one transformers and work with two, and we call this. But when we work with two transformers, we transfer less power, which is 58%. So those are the four types of the connection of the three-phase transformer. There is another point here which is maybe important in some cases, which is the phase shift. Okay. Some of three-phase transformer connection will be result a phase shift between the primary and the secondary voltage. So, in case of Y delta connection, the primary voltage and the secondary voltage, the secondary voltage will be shifted by 30 degrees from the primary voltage. So, consider here the Phasor diagram you are seeing here in the figure 31 of delta Y connection. Of course, VAN, which is the voltage phase to neutral. Okay, so here the voltage phase to neutral voltage, the phase voltage, here it's in phase with the output voltage, VA. So here we have Y, and here we have a delta. While the line voltage here, VAB, line voltage here, is shifted by 30 degrees from the voltage of the secondary. Here we have one voltage, we don't have ground, but here we can have two different voltage values. We have two different voltage values, but of course our source is connected line to line here. Okay, our source is connected line to line. So here a shift angle can be provided by this type of connection. So since delta Y delta connection provide a shifting of 30 degrees, also the connection delta Y also provide 30 degrees phase shift, line to line voltage. While delta delta or Y connection, we will not have this phase shift. So this phase shift is may be needed in such applications. For example, when we have there are some electric machines with more than 3 phase. In such applications, we may be need this phase shifting in the voltage. There are some machines with 6 phase. If we have, for example, a 6 phase machines, the first 3 phase and the second 3 phase must be shifted by 30 degrees or 60 degrees or what, or such an angle. So we can use those types of connections. So this is the last point in this part, which is the phase shift that can be achieved by these types of connection, delta Y or Y delta connection. And this is the end of our third chapter, the transformer. We have seen in the first part in this chapter the ideal, the construction of the transformer and the ideal transformer. And we have seen in the second part of this chapter the equivalent circuit analysis, the Phasor diagram, and the transformer tests. And we see in this third part some special cases or some special transformer which are the Autotransformer and the 3-phase the transformer. Okay, so this chapter may be the most important chapter in our module. I consider it. Okay. Next time, inshallah, we will try to organize 1 or 2 recitation sessions before passing to the 4th chapter, which is the DC motor. And this is my objective, at least to finish the 4th chapter which is the DC motor. If we have time, inshallah, we're gonna see the AC machines. Maybe at least we see the definition of those AC machines. But for me, if we finish the 4th chapter, I will be satisfied. For example, of course, for this level,